Come on in, you two. Got John and Micah. Come on in. Any questions? Go ahead. I've got about a minute before class starts. But like I said, you're welcome to ask me any questions. I'm just looking through the grade book right now to try to see if anybody's missing any tests. I see a couple people. That. All right. So it's about time to start class. No one's posted anything in the chat, and no one's actually asked me anything. But is there anything I can uh, help anybody with? Any kind of questions anybody has? I did notice I've got about 3 students that have missed tests in the past. Uh, that needs to be remedied, of course. I normally don't have to track my students down to get that. They normally know, but I know I had a couple students ask about things, but I've taken care of just about every student that asked, and I am being very generous right now to help people out because I don't, I want you guys to succeed, and I know I'm not perfect and I make mistakes, so I'm willing to help y'all out. So make sure you text me or send me an email if you have any issues with any of that, and let me know if anything I can do to help you. We're going to finish up chapter, I think it's chapter 9, which is chapter on momentum. I have 2-dimensional collisions to deal with, and then I've got some center and mass stuff to deal with, all of which hopefully you've heard a little bit about me talking about it, and you've actually been able to see some from the videos that I've posted online. So hopefully in your Canvas module for this week and last, you'll see some videos specifically. Most of them are lectures, but some of them are just specific problems and therefore shorter. But even some of the short problems are some of the shorter problem videos are still kind of long because sometimes it just takes a while to thoroughly explain a problem. So check those out. we're going to get started, and I'm actually using the e-text right now just to confirm that I was right about the chapter number, and I was. So today we'll finish chapter 9, which is linear momentum, and next time we'll jump right into 10. So it looks like no one has still sent me any kind of questions or anything, so I'm going to go ahead and get started. It's about 3 after, so let's get cracking. I'm going to start by sharing my screen. Then we'll turn my screen on because it might be helpful for me to see my screen too. All right. Hold on a second. Not working. Okay. Now let's see. Now I got it. Okay. So it should come up in a second. So I'm going to start off, instead of just showing you a generic equation for a generic two-dimensional collision problem, I'm going to start off with a very specific equation, but I'm also going to jump right in and explain something to you. So it turns out that, you know, if you actually know how to jump to a different coordinate system and stuff of that sort, then you can pretty much always make the case any type of collision, make the case that any type of collision that you want to study is essentially equivalent to one particle hitting another particle that you'd call the target particle, such that the target particle is sitting still and the initial moving particle is moving parallel to, say, the x-axis, because you can really orient the axis of the x coordinate, xyz coordinate system any direction you want. Not only that, if, for instance, you look out and you see one car going 40 headed north and another car going 30 headed south, then you can switch to the reference frame of the 30-mile-per-hour car. And in that reference frame, the 30-mile-per-hour car is sitting still. And in that frame, the 40-mile-per-hour car is going 70 miles per hour. So you can do that. And then you can align the axis to be parallel to that road. So you actually could align the axis parallel to the south, and you could make it like that. So in this case, let's imagine specifically whoa, I don't know how I ended up here. Anyways, let's imagine two specific particles. And in this case, we're going to take the two particles to be identical. I think that was what I had planned on. Let's see here. Yeah, that's right. Yeah, so we're going to consider pool. So let me draw the scenario. So we have a mass, which in this case is a pool ball. And that pool ball, of course, has a velocity v sub a moving in the positive x direction. So I'm going to actually draw a positive x axis and a positive y axis. Actually, I don't want to put the y axis there. Let me get rid of that. I don't like that one. I'll put the y axis right here. This is going to be my x axis. So I'll put it like that. And this is going to be my y axis. So I'll put it like that. And now what I'm going to do is place another ball right here. And that ball will be the other pool ball, but it's initially sitting still. Then after the actual collision, what'll happen is, let's say this ball moves off with a velocity VA prime at an angle of, let's say, 45 degrees, and I'll call that angle theta A prime. Now the other ball will move off with a velocity as well, and that velocity, whoa, Nelly, that did not go as it was planned. That velocity will be v b prime, and that velocity is at an angle negative 45 degrees theta I prime. Okay. Now they both have a mass ma equals mb is equal to just m. Now this collision is not necessarily elastic. I'm not going to make use of that, but what I'm trying to figure out is what is VA prime and what is VB prime. So what I'm going to do is I'm going to show you a way of solving this problem, and then you can use that in other similar problems where you only have two unknowns. And then I'm going to do the same thing with a slightly more complex two-dimensional problem and show you yet another way. So hopefully this will help. So here's my solution, which I shall write in red. So what we have is conservation of momentum, because our system includes two particles that are definitely going to apply a force to one another, but because the system includes them, those are internal forces. So we're going to start off with the assumption that the net external force acting on the system is zero. Therefore, conservation of momentum is a reality. So what we would have in general for the x dimension is we have m times VA is equal to m times VA prime cosine theta A prime plus m times VB prime times cosine theta B prime. And I'm going to go, I should probably mention this. VA is equal to, let's say, 5.00 meters per second. Okay. So this equation right here is essentially correct. What I want to do is just reiterate exactly which things we know. So I know that one, I know that one, and I know that one, but I do not know VA prime or VB prime. And in fact, I can divide through by M and all those M's disappear. I'm going to call this version equation 1. So here's equation 1 right here. Now I'm going to have an equation for the y direction. Notice the m sub a, which is just a mass m, of course, it actually only has the velocity in the x direction. So there, in fact, is zero momentum in the y direction. That means we'll have 0 is equal to m VA prime times the sine of theta A prime plus MVB prime sine of theta B prime. Again, Again, what we know are these things. So underlined variables are known. Okay. Now you can also see, just like we did before, that there's a common factor of m, since these two masses are identical, which would be, that could be the case, for instance, with pool balls. That could be the case, for instance, with protons. That could be the case with electrons. Basically, any particles, if you're having two identical particles running into each other, then by definition, they're supposed to be identical, so the masses should be the same. So because of that, I can go ahead and cancel out. Oh, I don't know why I keep doing this. I can go ahead and cancel out the m's by dividing both sides by m. And that actually gives us another form of the equation, which in this case will look like 0 is equal to VA prime sine theta A prime plus VB prime sine theta B prime. And that's going to be equation 2. So what I'm going to do is solve equation 2. In this case, we're going to solve it for VB prime. When I do that, I get VB prime is equal to, now notice they're both the same side and they're both on one side of the equal. So when I pull VB prime to the other side, it'll become negative. Or if I pull VA prime to the other side, it'll become negative. So the main rule is that we're definitely going to get a negative. And what we're going to have is VA prime times the sine of theta A prime. And then, of course, the coefficient of VB prime is sine theta B prime. So I'm going to divide through by sine theta B prime like that. And with this, I can get negative. And then we have VA prime. And then we have the sine of theta A prime, which was 45 degrees, divided by the sine of negative 45 degrees. And if you remember what your graphs look like from trig, I'll draw them right here just in case you don't. Actually, let's not do it there. Let's do this axis. I will do right here. And then this one I will do right here. So cosine looks like this. Whoa, Nelly. Let's take it off of auto draw because clearly it can't handle that. Cosine looks like that. And then, of course, looks like that. So you get that the cosine of negative theta is equal to cosine of theta. But sine looks like this. So you get that the sine of negative theta is equal to the negative of the sine of theta. So that's just what it means to be called an odd function. And this is what it means to be called an even function. And that comes in handy from time to time. For instance, if you're integrating over symmetric range, then an even function is the same if you integrate it from 0 to the end and multiply it by 2. But an odd function, if you integrate over an even range, is going to be, or excuse me, a symmetric range is going to be 0. So that comes in handy. What we get here, though, is basically that the sine of negative 45 is going to be the negative of the sine of 45. So we're ultimately just going to get VA prime times the sine of 45 over the sine of 45, which of course gives us that VB prime is equal to VA prime. So that's something helpful. We now know something specific. And now I'm going to take that, which I'll call equation 3, and I'm going to plug that into equation 1. So now plug 3 into 1. When I do that, I get VA is equal to VA prime cosine 45 degrees plus, now VB prime is just going to be VA prime again. So it'll be VA prime times the cosine of negative 45. And now you see why I actually took the time to do the cosine and the sine earlier, because this will become VA is equal to VA prime cosine 45 degrees plus VA prime cosine 45 degrees, which is equal to 2 VA prime cosine 45 degrees. So ultimately, I can say that VA prime, which equals VB prime, is equal to VA over 2 times the cosine 45 degrees. So that's going to be 5 4.00 meters per second divided by 2 times the cosine of 45 degrees, which you all know is root 2 over 2. But dealing with that, I'm going to say 5 divided by parenthesis 2 times cosine 45, close parenthesis again, gives me 3.53. And that's one extra sig fig, of course. And it's 3.535, so I should technically call it 3.54 meters per second. And that's with one extra sig fig. And that's our answer. Any questions on that? All right. Well, one thing you might notice here is if you look at the angle between the A particle and the B particle in that collision, after the collision, the angle's 90 degrees. This collision was not necessarily elastic. In other words, we did not tell you it was elastic. It may or may not be elastic, but I will tell you that one of the discoveries that we can make, and your book actually does do this as a specific problem. It was number 61 in the previous edition. I'm not sure what number it is in this one, or if they've even gotten rid of that problem from the 4th edition to the 5th edition. But the main thing is, it turns out if you happen to have a elastic collision in 2 dimensions where the target's sitting still and the initial particle's moving, then the 2 particles will leave at 90-degree angles separated from each other. So that's just a fact whenever the collision is elastic. So that's kind of neat, something you can use. So let's go on to another problem. Anybody? No one has any questions on this? Okay. All right, so let's do another problem. This time we're actually going to examine, let's say, 2 fundamental particles. Let's say 2 electrons or something like that. So 2 electrons collide with one traveling at 4.0 times 10 to the 5th meters per second, and the other standing still. Now, all this is subject to all sorts of debate from a quantum mechanical standpoint, but either way, we're just going to imagine 2 particles sitting, one particle moving towards the other at 4.0 times 10 to the 5th meters per second, and the other one sitting perfectly still. The collision is elastic. And one particle, whoa, evidently I was going to spell one with a W. And whoa. And one particle, or one electron, leaves the collision at 60 degrees above the x-axis. What are VA prime? Actually, I should probably do it like this. What are VA prime, VB prime, and theta B prime? And I'm calling it that, but to be honest with you, when the electrons interact like that and then they leave, there's really no way to tell which one went at the positive 60 degrees and which one went whatever direction it went. So it's slightly misleading to say MA is related, or excuse me, to say VA is the original one moving and VB was the one that was originally sitting still and all that stuff. But at the end of the day, it doesn't really matter. You just have two electrons leaving, and we're trying to figure out all the speeds. So let's do our solution like this. Again, we're doing conservation of momentum because we think the net force acting on the system is 0, and that's what's required for momentum to be conserved. So the x component of momentum is going to give us, again, we'll have m. Notice they're identical. So I'll say again that MA is equal to MB is equal to M. Okay. And the VA is something we know. That's the 4.0 times 10 to the 5th meters per second. And what we're calling theta A prime is equal to positive 60 degrees. So what I have here is MVA. That's the only momentum initially, and it's exactly parallel to the x-axis. So in the x component, we just get that. And then after the collision, we get MVA prime cosine 60 degrees plus MVB prime cosine theta B prime. Again, we really don't have any idea which one exactly is VA, or which one's A and which one's B. The main thing is we know they exist, and one's got to be one and the other one sort of has to be the other, but that's pretty much it. We also know that because their masses are identical, I can simplify this and make it into VA is equal to VA prime cosine 60 degrees plus VB prime cosine theta B prime. Okay, so I'm going to call that equation 1. Now I'm going to do the y component, and the y component is going to give us 0 is equal to m VA prime sine 60 degrees plus m VB prime sine theta B prime. Okay, again, we can get rid of the masses. So this is going to give us 0 is equal to VA prime sine 60 degrees plus VB prime sine theta B prime. Okay, that'll be equation 2. Whoa, no. That'll be equation 2. And now I've got elastic collision, and the fact that it's elastic means the kinetic energy is conserved. So that's that line right there. So we're going to write elastic, and this is going to give us basically 1/2 m sub a v sub a squared is equal to 1/2 m sub a v sub a prime squared plus 1/2 m sub b v sub b prime squared. And of course, now you can get rid of the 1/2 ma, 1/2 ma, and the 1/2 mb, because again, MA equals MB is equal to just plain M. So we're ultimately going to get VA. Ooh, I probably should stick with the black. We're ultimately just going to get VA squared is equal to VA prime squared plus VB prime squared. And I'm going to call this equation 3. Okay. Now, what I'm going to do is I'm going to take equation 1 and I'm going to bring VA prime to the other side and then square it. And I'm going to do the same thing with equation 2. So in equations 1 and 2, bring VA prime terms to other side and then square each side. Okay, so if I do that, what I'm going to get is the on number 1, which I'll write like this. 1 implies this. Basically, I'm going to get VA minus VA prime cosine 60, and then I'm going to square that. That'll give me VA squared minus 2VA VA prime cosine 60 degrees plus VA prime squared. And I need to make sure y'all know that that is prime and squared, not to the 12th power. So let me try to write that a little better. VA squared. And then the right-hand side, of course, will just be VB prime squared cosine squared theta B prime. And this is going to be equation 1 prime, say. Now for equation 2, it's a lot easier because there's really only one term on each side after I move them. So when I square the VA prime side, I'm just going to get VA. Ooh, I left off a big thing. Hold on here. Let me erase this. Everybody see that I left off something on the VA prime. So let me fix that. That's VA prime cosine squared theta A prime. And now that part's equal to VB prime. Ooh, that's not cosine theta A, that's cosine 60. Get your stuff together, Mr. Younger. Slacking off. Boy, that's a lot of stuff to erase. Probably should just erase it. All right. So this is cosine squared 60 degrees. And then the other side is going to be VB prime squared cosine squared theta B prime, like that. Now, let's go ahead and erase this part that I was doing. Now we're going to do the same thing to equation 2. So I'm going to bring the VA prime sine squared 60 to the left, and I'm going to write it over here for good reason. So I'll write VA prime squared sine squared 60 degrees is equal to VB prime squared sine squared theta B prime, like that. Now I'm going to add those two equations, and I'm going to make use of sine squared plus cosine squared equals 1. And when I do that, I'll get a nice reduction. So here's what it is. So adding 1 prime and 2 prime, we get VA prime, or excuse me, VA squared minus 2VA VA prime times cosine 60 degrees plus, now we're going to get in this term to be VA prime squared times cosine squared 60 plus VA prime squared times sine squared 60. Cosine squared plus sine squared is just equal to 1. So I'll just say it's VA prime squared. Same thing's going to happen on the right, only it's not the cosine of 60. It's the cosine and sine of theta B prime. So when I do that, it's going to become just plain VB prime squared. So that's the new equation that we had from combining those two. And I can take equation 3 and make it into equation 3 prime. And the way I'm going to do that is I'm just going to say that VA prime squared is just equal to VA squared. Actually, do I want to do that? I don't know if I want to do VA or VB. No, I want to do VB. That's what I'll do. So let me back that up. Instead of solving for VA prime, I think I'm going to solve for VB prime. That'll work out a little better. So I'm going to do VB prime squared is equal to VA. Whoa, no, my page just moved and messed up everything. Is equal to VA squared minus VA prime squared. That's going to be equation 3 prime. This right here is going to be the one that we just solved before that. I'm going to call this equation 4. So we're going to combine equation 4 and equation 3 prime. I think you can see that basically the VB prime is going to disappear. The VB prime squared is going to disappear and be replaced with VA squared minus VA prime squared. Let me see if I can copy this. I'm going to copy that. Now I'm going to paste it up here. Okay. So I've got that. Now what I'm going to do is I'm going to plug in three prime, and that'll give me VA squared minus 2VA VA prime cosine 60 degrees is plus VA prime squared is equal to VA squared minus VA prime squared. So that's where I've substituted equation 3 prime. Now you can see I can subtract a VA squared from both sides, and that looks pretty nice. And then not only that, I could, for instance, pull this VA prime squared over here and pull this term over here, and that's going to make both of them positive. And in fact, what I will get is 2VA prime squared is equal to 2VA VA prime cosine 60 degrees. That clearly has a extra factor of VA prime that can cancel out. It's also got an extra factor of 2 that can cancel out. And I'm finally left with VA prime. Oh, no, wrong color. I'm finally left with VA prime is equal to VA cosine 60 degrees, which is equal to 4.0 times 10 to the 5th meters per second times cosine 60 degrees. So VA prime is equal to, now I do my math, 4e to the 5th times cosine 60. And that gives me 2 times 10 to the 5th. So 2.0 times 10 to the 5th meters per second will be the velocity that the particle took off at 60 degrees above the axis will have. So we've got that velocity. Now I can also use, for instance, I can use 3 prime to figure out what VB prime will be. So now I'm going to say use 3 prime to find VB prime. So what I know is VB prime squared is equal to VA squared minus VA prime squared. So VB prime is going to be equal to the square root of VA would be the 4.0 times 10 to the 5th meters per second squared minus 2.0 times 10 to the 5th meters per second, and then that'll be squared. And that should give me ultimately 4 squared plus or minus 2 squared, which is 16 minus 4 gives me the square root of 12. I can work that out. I can say square root of 12 is 3.46. I'm going to call that roughly 3.5. So this one's going to be about 3.5 times 10 to the 5th meters per second. And that's my VB prime. So I've got 2 of them now. All I need now is theta B prime. So if I look back, I can try to find out what theta B prime is easiest to get from. And it looks like theta B prime comes out really easy if I use equation 2. So that's what I'm going to use. So from equation 2, we'll have 0 is equal to VA prime, which we found was 2.0 times 10 to the 5th meters per second times the sine of 60 degrees plus VB prime, which we found was 3.5 times 10 to the 5th meters per second times the sine of theta B prime. So that gives us the sine of, oh, don't know I wrote 3 there, but that gives us the sine of theta B prime is equal to the negative of 2.0 times 10 to the 5th meters per second times the sine of 60 degrees divided by 3.5 times 10 to the 5th meters per second. And we end up getting that gives me essentially negative 0.50, yeah, 0.50, which tells us that theta B prime is actually equal to negative 30 degrees, which is consistent with what I just told you a few minutes ago. In an elastic collision with identical masses, the 2 particles will leave at 90-degree angles. As you can see, the other one was 60 up and this one's 30 down. So 60 plus 30 gives you 90. And that's it. Any questions on that? No questions? All right, so now we're going to get into the slightly more complicated stuff. So let me start by explaining to you. Yes, go ahead.
Is that always the case? That it'll always be 90 degrees?
Yes, if they have the same mass, then what you'll see is if you look back here at this, let's say the elastic equation right there. If you look at equation 3, you basically have VA squared is equal to VA prime squared plus VB prime squared. You do know of one instance where that equation holds. Can you recall what that would be?
Can you repeat that last sentence?
Yeah, in equation 3 that we see right here, we have some quantity VA squared is equal to some quantity VA prime squared plus another quantity VB prime squared. Do you know of anything where, you get one number squared is equal to the sum of 2 numbers squared? It's a little abstract. Go ahead.
I'm drawing a blank right now.
That's okay. Yeah, it's one of those things. Once you see it, you'll be like, oh, no. But yeah, does that look like the Pythagorean theorem?
Oh my.
So
Yeah.
So yeah, it's like the VA is the hypotenuse of the VA prime plus VB prime. So that at least is a heuristic argument that VA and VB being perpendicular, or VA prime and VB prime being perpendicular to each other, is consistent with the elasticity equation. So that is more or less how you lock it down. And like I said, the book does have a problem at the end of chapter 9 where you can solve it to say that. I was actually still looking for the problem number, but I don't see it. Yeah, still don't see it. So maybe it's somewhere else. So yeah, that is a perfectly general result. Now you can see, for instance, I once tried to demonstrate this to my students, and I took them outside. This was I was teaching at a new school, and they had hired a student to clean out one of their equipment rooms over the summer, and the faculty member that had just quit and I was replacing had left already. So the poor student was unsupervised and just was asked to throw away a bunch of stuff. And I got there expecting to have, 30 years worth of lab equipment and stuff like that. And I'm not blaming the student by any stretch of the imagination. But when I got there, I discovered that there was a lot of equipment missing. So one day I had to do a lab and I was like, oh, wow, look, 2 bowling balls. I think I'll use that. So I rolled the 2 bowling balls. I took one, set it still, took the other one, which luckily was the same weight, and I rolled it. And sure enough, they left off at a 90-degree angle from each other, which was really kind of reassuring. And in fact, what I found out is the more quickly I rolled it, though, there became a problem because the ball would actually roll without slipping, and that would force the other ball to roll without slipping, and that actually caused a coefficient, if you will, of friction that was absolutely necessary and violated the elasticity condition. So the angle actually changed quite a bit the faster I rolled it. So that was kind of neat, but that's a case where the elastic collision failed specifically because the friction put in that's necessary to make a ball roll without slipping was enough to make the kinetic energy not conserved. All right, so now what I want to do is tell you about the next thing, which is center of mass. So ultimately, what we'd like to be able to do in a physics class or in an engineering program or just in nature alone is I should be able to just know something about the conditions that an object is subject to, and then be able to predict in the future what will happen to that object. So like if I take, for instance, a magic marker or a pen or this little center tap that I have here, if I were to take this thing and throw it, I would look at it and I don't really immediately see anything that obeys what we learned about projectile motion. What we learned about projectile motion specifically was that you can take y as a function of time, which is the quadratic equation. Remember, y is equal to negative 1/2 gt squared plus v0t. You can take that, and then you can take x, which is the x position of the projectile, which is the initial velocity times time. And you can combine those to eliminate time. And ultimately, what you'll get is y and x form a function that's a parabola. And that means specifically that when I throw this center punch, for instance, it should obey a parabolic path. But if you were to throw this or a pencil or a pen or a spatula or whatever, I bet you'd be somewhat hard pressed to find any part of that that actually obeys a nice smooth parabolic trajectory. In fact, there is something, and you might even know what it is already. Does anybody know of any particular part of a marker or a pen or anything like that that would follow a parabolic path? Again, a fairly vague question, so I completely understand if you're not getting it. Uh, if you and try this sometime on your own, take like a pencil or something that's really clearly marked, like a dry erase marker is pretty good because it has a really big E and an X and a P and an O on it. And you can let somebody throw it and it'll, naturally spin when they throw it. And what you'll see is there's one little spot on the pen that just rotates instead of translates. So like if the center of the X was the spot, then the P would actually circle around the center of that spot and make a weird shape. But the center of that X would in fact stay perfectly still while it rotated like that. That turns out to be the center of mass of the expo pin. So it is something that actually obeys the parabolic path, and that thing is the center of mass. And one of the definitions we use as the center of mass is the point in a body where the body acts as if all the forces are acting. Now, that's true until we get into chapters 10 and 11, where we start talking about rotational motion. But wouldn't it be nice that we could throw a marker and not only say, yeah, the center of mass is going to move in a parabolic path, but with a little bit of practice so that we know exactly when to release it from our hand and that kind of stuff. And we know exactly roughly how fast it would spin when it leaves our hand and stuff like that. We should be able to predict not only that the center of mass will go in a parabola, but also exactly what part of the pin is going to hit the ground first and stuff of that sort. So to do that, what you do is you sort of say, well, I don't see any reason for the acceleration or for the spinning to accelerate. In other words, the spinning should stay at roughly the same rate because air resistance is so negligible. So if we could figure out the typical rotation rate of a pin that Mr. Younger throws, then all we have to do is figure out what's the initial orientation of the pin about the center of mass when he releases it. So he could watch me a little bit and I could practice a little bit and so on and so forth, so that I consistently let it go at the same sort of orientation. And then I could use the time aloft to figure out how much rotation it would go through. And if I knew the total angle, I could just translate that to the final position of the pin, which maybe left my hand at this angle and maybe lands at this angle, not because it just did only that rotation. It probably did a bunch of rotation, but it ended up at that final state. So that's ultimately what we'd like to do. But in order to do that, we need to know, one, how to calculate centers of mass, and then we need to know how and what actually makes things rotate as opposed to just accelerate. So we've already learned F equals ma, and that tells us that a net force can cause an object to accelerate. But what would cause one end of the object to accelerate in one direction and the other end of the object to accelerate in another direction? Well, that's a new thing, and we're going to learn it. And most of you probably heard the word before. You've even heard of a special wrench with a name in it. Anybody think of what that term is that causes rotation?
Torque.
Yes, torque. So that's another thing we're going to learn. So with that in mind and that as the goal, let's go ahead and talk about center of mass. I'm going to, I think I didn't do that good a job earlier in trying to giving my students motivation for why these formulas are like they are, because really you need an understanding either of torque or you need a lot of experience in everyday life of turning wrenches and stuff like that. So maybe I just didn't explain it well enough because I'm more mechanically inclined than some other students, or maybe I just think about it too mathematically. I'm not sure. But let me tell you this. If you have an object and that object is made of a bunch of little parts, and maybe those little parts, which are quite heavy, are stuck together by something that's really, really light, like let's say a big plexiglass sheet. Okay. And then on the big plexiglass sheet, which might weigh a whole, half a pound or something like that, you have a bunch of 2-pound lead weights immersed in that plexiglass sheet. You might think, well, where on that plexiglass sheet would I want to point my finger so that I could balance the plexiglass sheet with all those masses on it? Well, that location would be the center of mass. And what you could do is you could treat the center of mass as if it's roughly some spot that you guess it is. And you call that the origin of the coordinate system that you're going to make. And then you just write out the X, Y, and Z components for each of the 3 particles or 4 particles or 20 particles there are. And what you'd see is sort of the bigger a mass is and the farther away that mass is from what you think is the center of mass, the bigger effect it has in causing it to tilt. So that might tell you, okay, well, I want to sort of balance out the product of mass and distance. And that's about all the motivation I think is reasonable to give you. So let me tell you the equation. The equation we'll be using is X center of mass is going to be, Remember, I told you the larger the mass is and the larger or the farther it is away from some specified center, the bigger effect it's going to have. So it seems that M1 times X1 would matter. And then you go to the next particle, which would be M2 times X2. And ideally, these things would be particles. But one thing we know from our gravity chapter is if these things are spheres, then they still behave as if they're particles, only the particles' coordinates would be the center of the sphere. So we can think of it that way as well. And we keep doing that, adding them all together until we've added up all of them, which is M sub n times X sub n. Now, that gives us a pretty good feel for the net effect of all them n's, but really we're trying to calculate a distance. The only way that seems reasonable to get a distance out of this is to divide by a mass, because currently we've got mass times distance, right? And there's no good argument to be made for any particular mass. In fact, the only good argument you'd make is all the masses combined. So what we're going to do is we're going to divide it by M1 plus M2 plus dot, dot, dot plus Mn. So that's the formula. And of course, there's going to be a similar formula. YCM is equal to M1 Y1 plus M2 Y2 plus dot, dot, dot M N Yn over, and this time I'll just say the summation from I equals 1 to n of M sub I. Okay, and then there's a similar one for X. So let's start off. I'm going to make up a problem that's a little bit more complex than the first example your book does. So let's make up a problem. I'm going to draw a coordinate system for starters. Okay, that's going to be my y-axis, and this is going to be my x-axis right here. And let's say we have a fairly uniform log. And I mean log like a telephone pole. Okay. And this log happens to float. And maybe we want to have it float in the water, and we're going to let a few people sit on it. So what I'm going to do is imagine that a person here will set, and that this position is specifically at x equals 1.00 meters. And I'm going to say this person's mass, M1, is going to be 50.0 kilograms. And then I'm going to go over here at the, let's say at the 8.00 meter mark. And I am going to say that a person sits here, and that person M2 or has a mass M2, and that mass is going to be 100.0 kilograms. And then I'm going to go right here and say this is 9.00 meters. And this person will be M3, will have a mass M3, and their mass will be 65.0 kilograms. And I will further add that this uniform log will have a mass of 300.0 kilograms, and in fact has a length of L equals 10.0 meters. Okay, so the reason I said it's a uniform log is what that generally means is if I took the whole rod or the whole log and weighed it and then divided it by the length in meters, I'd get a certain number of kilograms per meter. Let's say the answer is 5.00 kilograms per meter or something crazy like that, right? Now, if I take a single cubic millimeter of that log from anywhere in that log and I weigh it in kilograms, and then I measure its length parallel to where it was, and I divide that mass by that kilogram, by that length, I would get again 5.00 kilograms per meter. That's what I mean by uniformity. Okay, so the uniformly distributed mass means it's going to every little slice of it will weigh exactly as much as another slice of the same dimensions. Or even if you don't use the same dimensions, when you divide the mass by the length for each of those, it will always come up to be the same ratio. Okay. So with that in mind, that means the center of mass of the 300 kilogram log should be about 5.0 meters. So we're going to calculate the y center of mass. By the way, notice that the x-axis is what we would call a symmetry axis for the log. What I mean by that is if I took that log and just rotated it through any small angle whatsoever, it would look identical to before I rotated it. That means that the center, another center of mass, specifically the center of mass in the let's say in the z direction, would be actually along the x-axis. Okay, so when you have a high degree of symmetry like that and you can find a symmetry axis, then you know the center of mass is going to be on that symmetry axis. So let's go about calculating the center of mass. So the question is, or the problem is, find the center of mass. So in this case, you might actually say, well, what if I had somebody like Andre the Giant from The Princess Bride? And let's say Andre the Giant came up, and obviously this is even more strength than would than Andre the Giant would be capable of lifting. But if Andre the Giant were to grab it somewhere and try to walk and balance this with these people on it, he would want to grab it at the center of mass, because otherwise it would tend to rotate and flip over one way or the other. So that would be a usefulness of the center of mass. And we already know that the z center of mass would be right along the x-axis and the y center of mass would be right along the x-axis. So basically what we have is the y component of the center of mass is equal to 0 and the z component of the center of mass is equal to 0. We're just going to find the x component of the center of mass. So the x component of the center of mass will look like this. So what I'm going to do is I'm going to take first off the log, which is 300.0 kilograms, and I'm going to multiply that by its center of mass, which, as I told you, was 5.0 meters. Now, the next thing I'm going to do is take the mass 1, which is 50.0 kilograms, and I'm going to multiply that by 1.00 meters. And then I'm going to take the 100 kilograms, and I'm going to multiply that by 8.00 meters. And then finally, the 65 kilograms, I'm going to leave the units off here because I'm running out of space. The 65 kilograms times the 9.00 meters. And all that will be divided by the total mass, which I think you can see is 300, 350, 450, 515. So this should be 515.0 kilograms. So if I do this math, then I'm going to get, assuming I don't make any careless mistakes, 300 times 5 plus 50 times 1 plus 100 times 8 plus 65 times 9. And it looks like I typed everything okay on this. So that gives me 2,935. And technically, I should be very careful about my sig figs on this, just to try to match the homework system. So I'm going to look at this and say, okay, the 300 times 5, that's going to give me 1,500. And 1,500 would only have 2 sig figs. So that would really be a problem, because 1,500 only having 2 sig figs means we're only accurate to the hundredths place. So I'd have to basically take this 2,935 and just call it 2,900. So that's kind of problematic. The 50.0 kilograms times 1 meter would in fact give me, and I'm trying to make sure everybody knew that was a decimal, but I made it actually worse. But if I took the 50.0 meters or 50.0 kilograms, multiplied that by 1, that's going to give me a 3 sig fig number, which is 50.0. So that one gives me the 1 decimal place. The 100 kilograms times the 8 meters gives me 800, and that's 3 sig figs because of the 8. So that would only give me to the ones place, and the 65 times the 9, that would be a problem as well. So I'm going to have to throw caution to the wind and assume that it has that that 4 sig figs in the top, when in reality it looks like I screwed myself up by calling it 2935. But let's go with it. 2935. I'm going to divide that by 515, and that gives me 5.699, which I'm going to call 5.7 meters. Notice how the kilograms canceled out nicely. And in reality, what I've just done is I really used the appropriate significant digit rules by using just 2 sig figs. So that's a pretty good estimate. And what you see there is the fact that it's so close to the center is basically because the log is the heaviest thing by a factor of 3 on it. So that really has the biggest effect. That would tend to keep the center of mass very close to the 5 meter mark. And then that little 50 is going to be somewhat counteracted because it's 4 meters over. But then the 65 is 4 meters over the other way, and that's about 15 kilograms more. So you would expect it to be just a little bit further to the right of 5.0. But then you see 100 kilograms that's 3 meters away from the center, and that's going to make it even more. So that's why we ultimately got 5.7 meters. Anybody have any questions on that? All right, so that's a pretty decent example of calculating the center of mass. And it's not completely different from the one your book does. Your book does it for one of those inflatable banana log boats or whatever. I just did it with an actual weighted log. So now let's go ahead and try another example. This one's going to be at least a 2-dimensional example. So let's imagine, for instance, that again, I'm going to have a coordinate system. The coordinate system is not something that you necessarily have, obviously. Generally, what's going to have to happen is you as the student, or you as the engineer, or you as the physicist is going to have to assign a coordinate system and then use that coordinate system, and preferably the best coordinate system you can come up with, and use that to do all the calculations. So what I'm going to do is I am going to say that there is a ball at the origin, and then over here at about 2 meters away is another identical ball at the origin, and then up about 1.5 meters is another ball. And oh, that ball got ugly. So it's going to be another ball like that. Okay. Now, what I'm saying here is this little dimension, this little dimension right here is 2.00 meters. This dimension right here is 1.50 meters. And the other one's right at the origin. And I'm going to say each ball has a mass of 5.00 kilograms. Okay. And what we can imagine is we could imagine that it's actually sitting along on a really, really light sheet of plexiglass or something like that. Nice, rigid, very strong, but essentially massless. And then you basically want to figure out where I could put my finger on this piece of plexiglass to balance these 3 weights. So that's the answer to the question. Now, I would guess it would be maybe 2/3 of the way from the 0 to the 2 going left and right. 2/3 of 2 is 4/3, so that's about 1.33. So maybe I would estimate XCM estimate is about 1.3. And I would probably say, since there's a lot more weight down here at the bottom than there is at the top, that I'd only be about 1/3 of the way up the 1.50. So this should be roughly around 0.5 meters as YCM estimate. Okay, so that's just my guess. But I'm going to go ahead and calculate. And the reason why you do that is John Archibald Wheeler used to say, never solve a physics problem whose answer you don't already know. And that's a really good practice, because you are basically applying the scientific method and learning to apply physics. So you're using your knowledge of mechanics and nature and physics as you know it to make a guess at the answer. And then you're going to actually calculate it. So you get a chance to actively see whether your intuitions were right and correct them if they're not, or to pat yourself on the back for being so wise. So anyways, we'll go with that. All right, so here's the solution. So the center of mass in terms of X is going to be the first mass, which, by the way, all of them are 5 kilograms. Oh, well, that was bad. All of them are 5 kilograms. So I'm going to just factor that out just from the beginning and just call that 5.0 kilograms. And then the first mass is at 0. And then the second mass is at 2.00 meters. And then the third mass is also at 2.00 meters, at least left and right. And then the total mass, of course, is 5 plus 5 plus 5, which is 15.00 kilograms. So basically we have 4 times 5, which is 20. So this is 20.0 kilograms meters divided by 15.00 kilograms. Obviously, that's 4 times 5 over 3 times 5. So that's 4/3, which actually I got really lucky and got it exactly right. So that's 1.33 meters is the X center of mass. So I got a lot luckier than I did earlier today. That being said, I did actually solve a problem very much like this in class today. So maybe that's where maybe I learned it. I don't know. Maybe I'm cheating by accident. Anybody have any questions on that? All right. So the next part is Y center of mass. Oops. And the Y center of mass will be done the same way. And I'm going to say 5.00 kilograms. This time, the first particle has a Y coordinate of 0, but the second particle also has a Y coordinate of 0, and the third particle has a Y coordinate of 1.50 meters. And then, of course, all that's divided by 15.00 kilograms. So 1.5 times 5 should be 7.5. So that's 7. So that's 7.50 kilograms meters over 15.00 kilograms. And in fact, I get YCM is, again, exactly what I guessed, which would be 0.500 meters. Any questions on that? All right, now we've got about 8 or 9 minutes left. I'm going to do a more robust problem, and I will tell you that in general, if you can cut the individual masses up into infinitesimal size, then the X center of mass would equal the integral of X dm over the integral of dm. The Y center of mass would equal the integral of Y dm over the integral of dm, which is the total mass. And of course, the z is the same way. But I'm going to give you a caveat that basically dm will be either lambda times dl, meaning it's basically a one-dimensional object. So you really only need one coordinate like lambda of x to tell you how the mass varies along the x-axis. So if you're talking about a bicycle spoke, for instance, that would be a really good one-dimensional object. Or if you're talking about a 15-foot long a log, for instance, then the diameter of it being on the order of 10 inches means the diameter is so small compared to the 15-foot length that it essentially is, again, a one-dimensional object. So that would be when you'd use that. If you have a two-dimensional object, which would maybe be like a sheet of plywood rarely has even a whole inch of thickness. It's much more normal to get on the order of 3/4 of an inch, even for the stuff for your floors. And then it's 4 foot wide by 8 foot long. So that's really way bigger in two dimensions than it is in a third. In that case, you would use sigma times dA. Or if you truly have a three-dimensional object, then you would use rho times dV, where V is the volume. And I will let you know that lambda should have units of kilograms per meter. Sigma would have units of kilograms per square meter, and rho would have units of kilograms per cubic meter. And when I say uniformly distributed mass, what I mean by that is lambda r, sigma r, rho is equal to a constant. Okay, so I'm really running sort of short on time, so let's do one. I'll try to do two complicated ones. Let's see. So let's say this is my x-axis, this is my y-axis, and let's say I have a rod, and I think you can see that the in and out of the page dimension of this is very small, and the up and down dimension is very small, but the left-right dimension is big. So this looks like a one-dimensional object. What I'm going to say is that the density, the line density, is equal to lambda 0 at x equals 0, and it's equal to 4 times lambda 0 at x equals L. So I'm basically making the conclusion that this is a length L, and I'm also going to say that its mass is M. Okay. What I'm also going to tell you is that the linear density, not related to linear equations in this particular version. So the linear density is linearly, now this time it is linearly related. I don't want to put the word related there, so I'm going to linearly related to x. Now, in my world, what that means, and again, I'm a nerd, so I think a very specific way, which may not be the way that you think. What that means to me is lambda of x is equal to some slope times x plus some y-intercept. And because of that, I can use that to figure out what m and b are. I can say, for instance, lambda of 0 is equal to lambda 0, which means lambda 0 is equal to m times 0 plus b, which means b is equal to lambda 0. I can also say that lambda of L is equal to 4 lambda 0. So that means 4 lambda 0 is equal to m times, in this case, it's L plus we already figured out what b was, so that's going to be lambda 0. So now I can say, oh, well, lambda of x must be equal to, notice if I subtract lambda 0 from both sides, I get 3 lambda 0, and then I divide by L. That means the slope is 3 lambda 0 over L. And then the equation is y equals mx plus b. So that means y equals mx plus b gives me 3 lambda 0 over L times x plus lambda 0. And we only got about 2 minutes left, so I got to rapidly go through this. So what I'm going to do is I'm going to say this is my little differential mass element. And I can get that by multiplying lambda of x times dx, because the width here is just dx. In other words, my integrand doesn't vary very much over the x coordinate. So my calculation of the integral of x dm should go pretty well. So I'm going to take the integral from x equals 0 to L of x times lambda, which is 3 lambda 0 over L times x plus lambda 0. So that's my lambda of x times dx, which gives me integral from 0 to L of 3 lambda 0 over L x squared plus lambda 0 x dx, which I think you can see when I integrate x squared, that's going to become 1/3 x cubed, and then I evaluate it at 0 and L, it's just going to be 1/3 L. So I'm going to get lambda 0 over L times L cubed. Obviously, one of those L's is canceling out. Now, when I do the integral of lambda 0 x, that becomes 1/2 x squared, which becomes 1/2 L squared. So I'm going to say plus lambda 0 over 2 times L. So I can cancel out, for instance, this guy with this guy, and that's going to give me 1/2 lambda 0 times L plus 2/2. So that's 3/2 lambda 0 L. So that's what the top integral is. The bottom integral, the integral of dm, is just the integral from 0 to L of 3 lambda 0 over L x plus lambda 0 dx. That's going to give me, instead of x cubed, because now it's just the x to the first power, that's going to give me 3/2 lambda 0 over L times L squared plus lambda 0 times L. You can, of course, cancel out that x squared with this, and now I got 3/2 plus 2/2 is 5/2, and this will give me, in fact, 3/2 plus 2/2 is 5/2. That gives me 5/2 lambda 0 L. So the x center of mass, which is equal to the integral of x dm over the integral of dm, is equal to 3/2 lambda 0 L over 5/2. Oh, this was supposed to be, oh, that was supposed to be L squared. Oops, let me fix that real quick. This one was supposed to be squared. That would be squared. Everything else is fine though. So I put a square there, and you see what's going to happen is this will cancel out with this, because that 2 is lambda 0. And then this 2 is going to cancel out with that 2. And I'm just left with 3/5 L. Okay, and that's the center of mass, and time is up. So you folks are free to go. You can find several other examples, including triangles and stuff like that, on my YouTube channel. I'll put videos. I'll make sure some of those are on your manual as well. We're basically done with chapter 9. We'll start chapter 10 next time. Have a good day, everybody, and thanks for coming. And let me know if there's anything I can do for you. Start practicing for that midterm that's coming up, second midterm.
Speaking of that midterm,
Yes.
I was late to the last class, and then everybody said there was an announcement about the midterm and the date of it.
Yeah, the midterm was supposed to be you guys meet on Mondays and Wednesdays. So it was supposed to be this past Monday, or no, it's supposed to be this coming Monday. So you're just getting at your regular time. Because the Monday lab was already a week behind everybody. So there's no change for yours, right? Your lab does meet on Monday, or does it meet on Wednesday?
It meets on Monday, but I was looking through Canvas and I didn't see anything on there about when that test is. Am I mistaken?
Yeah, it's next lab. It's during lab next time.
I didn't see it on Canvas. That's why I'm
Let me
confused.
check in the modules. I think I made the announcement in class, and I thought I sent another announcement out, but you can see practice second midterm chapters 1 to 8, November 1st. So
Yeah, I saw
yeah, November 1st is supposed to be the day. Is that Monday or is that Wednesday?
that.
Actually, I think
that's Wednesday.
yeah, I think that's Wednesday. I was supposed to put that on the 30th, I guess then. So yeah, the exam is supposed to be this coming Monday. So your very next lab meeting, and y'all meet lab after class, right?
Yes.
Okay, that's when the test will be. I'm going to try to make it as user friendly as possible. I would definitely recommend you focusing on taking a bunch of those practice tests as many times as you can to prepare for it. And of course, you can ask me questions in class beforehand if anybody needs. I'm supposed to start chapter 10, but in light of you specifically, I don't know that anybody else had the problem, but in light of you specifically having not known about that, I'll certainly be a little bit more inclined to offer you guys assistance during class as opposed to worrying about jumping ahead to the next chapter.
And that covers chapters 1 through 8, correct?
Yes, 1 through 8.
Okay. All right. I have a lot of work to do before I get to chapter.
I might even be able to, if you guys want, I might be able to slide on like maybe 20 minutes early or something instead of 5 o'clock, instead of 5:20. I could slide on at 5. If someone would just text me, let me know they want to do that, then I'll make sure I do it by 5 instead of 5:20. If no one texts me, I'll just show up at 5:20. But yeah, definitely text me. You can wait till Monday. The earlier in the day Monday, the better, but definitely text me on my phone. I'm going to send that to you as a chat message right now, just in case you forgot my number and I don't want to put it on the interweb. So I don't want to send it to just one person. So there's my cell phone number. Just text me if you would like me to show up 20 minutes early. That'll give you some more time in case you have some last minute questions. Of course, you can also text me over the weekend. I'll answer as many questions as I can too.
Okay. All right. I appreciate it.
Good luck. Thank you.
Thanks.
That was the last of them.